It's almost time. It's almost time. Wait for it. Wait for it. Wait for it. How do you like the music in the background? Hey there, Catherine. Nice to see you in the chat. Saw you earlier too for a brief moment. Uncle Bill in the chat, painting it yellow. Nice to see you there too. Trying to learn to look at the camera and not my screen. See, the camera's here and the screen is here. So if I look at myself on the screen, it's a little funky. So I need to sort of angle my glasses so I'm not like that. Right? It needs to be down a little bit so you all can see me. So I'm having to look to sort of the top of my glass. These are all things I've just got to learn. So hey there, it is 2 hours UTC. It's time again for Astronomy Daily Live. So come on in, friends. Take a seat around the circle of friends here, the ever-growing circle of friends. You can also call it sort of like a virtual porch, right? It's a porch where, right, and the sun is setting as it is now. You can probably see the sunlight on the face here, and that should be going away pretty soon. Yeah, sunset is imminent. Sunset is imminent here in southeastern Arizona, United States. So welcome, welcome. Come on in. Come on in. We're getting ready to talk astronomy for an hour or so. Now, as you can see, I've reconfigured things a little bit. Couple of past live streams have been a little funky in terms of the laptop. So the laptop was getting warm. It was being overtaxed. It was really having a pretty rough time. So decided pretty much last night that it's like, you know what, I need to utilize. I've got 3 Linux machines here, right? All running. Actually, I think let's see. The one that is running this is Fedora 26. Sort of my working machine is Fedora 24, which I still need to update. And then my oldest machine over there, I think that's Fedora 2, but I'm man, I want to say it's like Fedora 14, something like that. It's never been updated. I should probably update that. Probably a good idea. Probably a good idea. Now, there's some problems with this Linux machine that I've noticed. One of the things that I noticed pretty much right away is that I can't use my mic. So I'm using the camera mic instead, and I did a pretty extensive test just a little while ago, and I think the sound is okay. It's okay, and I can play some music in the background. This is Beethoven. So you know, I don't know if that's a copyright thing or not. At this point, I'm not going to worry about it. We'll see what happens. That's all I can say. Now, if the audio is really, really bad, like in terms of you can't hear me, or if the music is too loud or anything else, let me know. I do have a fan running on the Linux machine because it was getting pretty warm there during my testing. So I've got I've got a fan on it, and it's nice and cool. So I've also got, as you can probably see, this wide field of view. You can see right here, this is my smartphone, and you're watching me. So you got me here, and you got me here. So this is just how I monitor things. And I'm going to point that up just a little tiny bit, just like that. Okay. It's a nice wide field of view. Now, one of the other problems with this configuration is that I have no control over my exposure time, brightness, contrast, anything at all. Can't change the focus, can't do anything. So it's all automatic. Whatever the camera thinks that it wants to do, it's going to do. I looked around briefly to see if there was any Linux software that talked to a Logitech C615, and on a preliminary search, I did not see it. And I have to remember to look at the camera, because there you are, right there. You're not down here, you're up there. So yeah, I've got to get used to that a little bit. That's pretty fun. So I haven't seen Bobby coming in as a panelist yet. I thought I sent him the link. Let me look really, really quick, make sure that I sent him the link. See, what the other cool thing about this is that I've got everything right here. I don't have to switch between machines or anything like that. Just want to make sure that I email Bobby the link. I want to make sure that I did that. Yep, I did. Okay. All right. Well, hopefully he's all right. So yeah, welcome everyone to Astronomy Daily Live. It's now 2:06 UTC on the 4th of August, 2018. It's just flying by. It's just flying by. So cheers. We've got the hydrogen hydroxide here. Is it getting a little loud? It seems a little loud to me. Since Bobby isn't on here, I'm going to take the headphones off for now. And, of course. Bobby, the second I took my headphones off, because it's like, well, Bobby isn't here. So, I mean, I literally took them off, was going to put them here, and you popped in. So I know you're planning those kinds of things.
Yeah, but some.
Okay, I can't hear you.
Dead. Somebody.
How about that? No, I can't hear you, Bobby. So, yeah, this new setup has a little bit of limitations and a couple of kinks that I'm going to have to work out, I think. So, but we will. Let me see. Yeah, you're not muted or anything. Actually, I'm going to turn me down as well. I think turning me down a little bit was really nice. And people in the chat are going to have to let me know how the audio is, how the video is. Is this music too loud? And Bobby, I cannot hear you. Let me
Testing 1, 2.
We're going to be doing astronomy, but let me check one quick thing, see if I'm just plugged into the wrong thing. Hold on one sec. Yeah, Bobby, I don't think I'm going to be able to hear you.
Testing,
Let me
1,
look
2.
at my settings really quick and see. How about that? Try saying something, Bobby.
Testing 1, 2. Testing 1, 2.
Don't hear you at all. Yeah, and that's me. That is definitely me. All right. Well, I'm gonna just go with it for now. Just know that I'm not gonna be able to hear you at all. So I'm gonna take those off. So cheers. So yeah, I hope everybody's doing well. I'll work out these hardware things. This machine I really haven't given a lot of attention to, so it's lacking in a couple of areas. So yeah, I'm going to work on that this weekend and see if I can't get it sort of better operational, because yeah, I mean, Bobby's nice enough to come on here and can't hear you, so, and that's my bad. So my apologies. Stick on here if you want, Bobby. You can talk over me if you want. I won't know the difference.
Yeah. Can you?
Yeah. Chat should be able to hear you. Oh, and Bobby's a lot lower than usual. Well, I can fix that. I can definitely turn Bobby up a little bit. So, yeah, it's just, I mean, it's going to be a little weird if we're both talking at the same time. So yeah, my apologies in terms of that. But this is part of trying to get better, and sometimes it's like better, 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 better. So sometimes there's a little bit of a dip. I'm just going to go with it. So cheers. So every single day, starting at 2 hours UTC, we come together and we talk astronomy for about an hour or so. And I'm here to share a passion. That's it. Not necessarily here to communicate science or try to get people interested in astronomical things or scientific things. I think if you're here, you probably are already interested and just want to hang out with like-minded folks, and that's what this is. So very informal, very casual, very fun. But just we forget about everything else, right? TV is off. Forget about all the news, and let's just sit here and think about the universe, which man, that's enough, isn't it? Is the background okay? That sound pretty okay. Try the headphones again. All right, I will. But yeah, I think it's all on my end.
Test 1, 2. Test 2. Test 1. Test 1, 2. Test 1, 2. Test 1, 2.
That's all right. That's on my end, and hopefully, probably, I'll be able to work that out. It's just, yeah, I didn't think of that part when I was messing around here a little bit earlier. So no worries. We'll get through it. All right. Well, what I thought that we could do today is I don't think that we've done an object of the day in quite a while. And you know what? Yeah, cool, cool. Very, very cool, Bobby. Thanks. Um, uh, I think we could do a object of the day, and let's do a Messier object instead of a NGC or a constellation or anything. Let's just do a Messier object, and yeah, let's sort of see where that goes. So I did confirm that I can share my screen, which you know, if I couldn't have shared my screen, this whole thing sort of would have been a showstopper, and you would have seen just what you normally see. But I can share my screen. I can actually share a screen. So I'm going to share my Chrome screen. And so the Messier objects are a collection of 110 non-stellar objects, right? So those are galaxies or globular clusters or open clusters or planetary nebulae or gaseous nebulae. And these were cataloged by Charles Messier back in the mid 1700s. So quite a while ago now. Like, wow, like 300 and, wow, is it, no, 250 years ago. So yeah, pretty long back. He was a comet hunter, and so he was looking all over the sky anyway, and he came across these objects, these things that you know, sort of looked like comets, but they didn't move. So so he wrote them down. He wrote down the positions of them, and I think they were sort of on his, at least, you know, do not observe list. You know, if you come across this, look on the list. If it's there, skip it. Well, it turns out that these are some pretty spectacular objects, right? They're sort of the brightest non-stellar objects in the sky. Now, at least one of them is sort of like, I don't know what Mr. Messier was seeing, but oh, excuse me, but it's M72. M72 is a collection of 3 stars, and I don't know if they're associated with one another or not. Not exactly sure, but everything else is pretty spectacular. So I've gone over to random.org, as you can see, and I'm going to have it generate our Messier object of the day here. So let's see what it's going to be. You ready? Okay, here we go. Boing. Oh, M25. That's a nice one. So what I'm going to do is I'm going to, this is kind of cool that you can see all of this. Now, I don't think I've got Sinbad over here yet, so I'm going to have to do that. Oh, and this is going to be so much nicer because this mouse actually works, right? On the laptop, the biggest problem that I have with that stupid laptop is that the mouse pad didn't work. Every single time I tapped the mouse key, it would register 2 clicks, and that just wreaks havoc, right? All right, so M25. The funny thing is that I was testing this out earlier, and it's like, wow, I'm going to be able to share Stellarium. And so I installed it and started it up, and nope, I can't. You know what? I'm going to try one more time, just because I can. and see if, now this is going to be sharing the Google Chrome screen, but what I can do is I can, how do I, it's F11, I think, yeah. So what I can do temporarily is I can stop sharing. I'm just going to try this really, really quick. You guys all have to be my guinea pigs. So I'm going to share. Yeah, Stellarium is black. Yeah, that's just not going to work. It's not going to work. Right? That's totally black. I think that is just going to be totally black. Yeah, totally black. Okay. All right. Well, I'll work on that too. I'll work on that too. No worries. No major worries. So let me, I'm going to share Google Chrome again. Hide that. Oh, here we go. Come on. Okay, so here we go. Now, that is not what I was looking for. We want Messier 25. Let's just type it out. Well, maybe this is Messier 25. It just has another name. So they're calling it IC 4725. That is M25 for sure. Okay, all right. Caught me off guard there a little bit, but that's all right. I'm going to pop up the chat here so I can. It's going to be a little hard for me to see both the chat and this at the same time, but I can do it. I can do it. All right. So let's see. He's very, very much embedded in the galactic disk, right? He's got a right ascension of 18 hours, 31 minutes, 47 seconds, and a declination of negative 19 degrees, 7 minutes. But you can see the galactic coordinates here. So 0, 0, galactic coordinate would be the center of the galaxy, right? And then a plus 90 is the north galactic pole, and a negative 90 would be the south galactic pole. So you can see that it's, what, 13 degrees east, 13 degrees east of galactic center, and 4 degrees south. So actually pretty close to the galactic center. Looks like our relative velocity shows that it is moving away from us at a pretty good clip, 61.2 kilometers per second. Yeah, that's not incredibly fast or slow, not really. A couple of magnitudes here. The B filter, B as in boy, and then the V filter, V as in Victor. So you can see that both in B and V, our eyes are sort of most sensitive to V. Bobby, I don't have a Windows 7 machine here at all. The machine that you're hearing in the background playing Beethoven is actually Windows XP. All right, so let's skip down here and sort of see. So there's a bunch of different names of this object, including Messier 25. You know, I'm really having a problem. I thought Messier 25. You know, I have to check this out a little bit. 'Cause I thought M25 was something else. D25. No, it's an open cluster. Okay, all right. I knew that it was in Sagittarius, but I thought it was a globular cluster. All right, all right, all right. I will. I'll back off. I'll back off. Yeah, just a pretty loose association. The thing that sort of got me thinking that maybe we're not looking at the right thing is the number of references, right? It's like, for being a Messier object, there's not a lot of references. Now, 176 is still quite a few, right? But it's not thousands. So, interesting. Well, let's see. Let's see. We've got a distance measurement and a proper motion measurement and a metallicity measurement. I heard a funny thing the other day. As far as astronomers concerned, there is hydrogen, there's helium, and there are metals. So they can look at the spectra of these objects and look for iron lines, Fe, and they can look for hydrogen lines, and they can measure how much iron there is and how much hydrogen there is, and then they look at the ratio of that, and that is a measurement of what astronomers call metallicity. It's just how much stuff other than basically hydrogen and helium there is. I think what I'm going to do, I'm going to listen in on my smartphone here since I can't any other way. Okay, that's pretty good sound. Okay, so let's take a look at those. So 620 parsecs. I'm going to grab my handy dandy calculator that even though I completely rearranged my desk, I still have my calculator within arm's reach. So 620 times 3.26. 3.26 is how many light years there are in a parsec. So 620 times 3.26. So that's about 2,000 light years. About 2,000 light years away. Pretty cool. So the proper motion is usually measured in arc seconds per year, and they can measure it in both right ascension and declination. I'm thinking, I'm not quite sure what this ME is. That might be like an error measurement. Not quite sure, but it looks like it is moving in the negative sense in RA, so it's getting smaller and smaller and smaller. So it's moving west in RA, and then it's moving south in DEC. And we're going to have to see, this is, I guess this would be sort of a collective motion, but because it's an open cluster, right, probably each of the stars is sort of moving in its own way, but collectively, all these stars are moving in the same way. And that's actually how you can identify members of clusters, is you can look at their motion and, look in a field of view. And we'll actually do that. We'll go over to the HST archive and look at this. Look at the field of view and measure the motions of all the stars that you see. And when you sort of, look at those details, what you'll notice is that some of the stars, maybe a dozen, maybe 100, maybe 1,000, maybe a few thousand, in terms of a open cluster, will all be moving pretty much in the same direction at the same speed. And that's because the theory is that all of these stars formed pretty much together at the same time. So before they were stars, they were a clump of gas and dust, and so yeah, they've been moving with each other for a very, very long time. Now, as the theory goes, eventually they sort of spread out, right? So the fact that they're in a cluster still means that those stars are still pretty young, right? I mean, take a star like our sun, right? Our sun, as far as we know, isn't associated with any kind of a cluster, right? It's sort of a solo star, but presumably it formed in a large cloud of gas and dust with other stars. So the guess is that our sun does actually have some siblings out there, but I don't think anybody has figured out which ones those are. One would think that that'd be pretty easy, but yeah, for some reason, I guess that just hasn't been done yet. And as far as metallicity goes, that's kind of a it's kind of a funky number. They do give a reference. I wonder if we can get a better number for that. Part of this live stream is just sort of following our noses. I don't have any set plans or schedules or anything. This is curiosity, and this is inquiry, and we're just trying to follow our noses. And when I see a measurement that says 0, I'm sort of like, that's not very fair. So, but there's a paper. Let's go see. Let's go see if we can find the actual number. It might be just a really, really, really small number. So we'll go over to ADS as we usually do, and we'll look at this. Oh, I don't know. Do I have a PDF viewer? Oh, apparently I do. So on the metallicity of open clusters. All right. Well, let's see if is Messier in here. Nope. How about M25? Nope. How about IC4725? Aha, there we go. So it's essential to compare the metallicity scale of the open clusters and the Cepheids. Okay, I'm not going to go in that direction. Anyway, there's our guy, right? IC4725 is M25, so we've got him. He's mentioned again. Let's see if we can get some numbers. Here we go. All right, this is going to be kind of hard to read. Can I rotate this? I should be able to rotate this, can't I? There we go. So IC4725. Look at that. Is that it? Look at that. In the paper. In the paper, it's 0. What are these other numbers here? Okay, so radius, I guess. Range, maybe? Kiloparsecs? Yeah, that might be radius and age. So yeah, very, very young, right? 60 million years old, it says. 60 million plus or minus 30 million, because this is in giga years, right? Billions of years. So you got to move your decimal point over 1, 2, 3. So that'd be a 60. Yeah, so 60 million years. And they're saying 7.41 thousand parsecs. Let's see, 7.41 So 7,410 times 3.26. I don't think it can be wider than it is far away. So let's see if there's a... They measured quite a few of these. Yeah, they don't give number of stars used in the calculation, total weight of the photometric metallicities. The last column indicates the number of studies. So, they even... Oh, okay. Used to calculate the mean distance from the sun and the age. Okay, so wow, they're actually saying that this is... Oh, where is it? So they're saying 7.41 thousand parsecs. So that's quite a bit further than what we're seeing here. So, interesting. Interesting that there's such a discrepancy. But anyway, it's pretty cool to see. And this is what I like, right? I like to be able to, do this, go, that's a little strange. Let's look at the paper, right? And there it is. And strangely enough, so yeah, what is that saying? This is a logarithmic scale, right? It's the log. I think it's the log of the of this ratio. So a log of 0. I don't think that. I'm gonna have to think about that. I don't. Yeah, see, there's a couple. It's kind of funny, right? There's a positive 0 and a negative 0. So they've got some kind of measurements here. And maybe I'm reading this completely wrong. Maybe I should be looking. Yeah, I'm not sure now. Let's look at the HQS, LQS, and weighted photometric metallicity. So yeah, I think that has to be the photometric metallicity. But yeah, for our guy, we're showing a 0, which is just a very, very, very small number. So either they're not seeing anything at all, or it's just very, very, very small. So that's kind of interesting. I'd like to see a plot of these. I wonder if there is a plot. Metallicity plot. I didn't see one. Let's see. Whoop. Oh, we're upside down now. Let's see. I think let's get some text here. There we go. Okay. There we go. Okay. Are we gonna? That's not too interesting. Okay, so here's. Yeah. It's not going to talk about our specific guy. All right. Well, let's move on. Let's see what other interesting papers there are. Plots and images. Oh yeah. Let's look at a picture. Of course. We look at the chat really quick, make sure that there isn't any. Okay, good. Okay, so we'll zoom out a little bit here. Let's see if anybody else has looked at it. I don't see anything there. Well, let's. Oh, DSS2. So yeah, we're looking at quite a few stars here. We're looking right into the galactic disk. So yeah, there's going to be a massive number of stars. Crazy. But you can see very, very clearly that there is a nice concentration of stars there, and they're all sort of brighter, and they're closer than these background stars, so they are going to look a little bit brighter, more spread out. Here, let's back up a little bit more. Yeah, so you can see that there's a concentration there, right? It's sparse. It's definitely sparse. Don't know if these guys are associated or not. Probably not. Probably not. Is that audio too loud? Let me know if the audio is too loud. It seems a little bit loud to me. So let me know. All right, well, cool. Yeah, there's a couple of stars in this field of view. And as I said, what they can do if, like Gaia, right? Gaia most likely has measured the positions and motions of every single one of these stars, right? I mean, as long as it's able to pick it out, it can be able to do that. And so what you can do is you can look at the motions of all of these stars, and what you'll notice is that this star and that star and this star and this, all of these bright ones probably are moving about in the same way, and nothing else is. Not at least exactly in the same way as these, right? These are all going to look to move sort of the same way. Oh, let me restart the music here. There we go. All right, well, let's zoom out even more, just for fun, and just see what's around. We're in Sagittarius. Looking pretty nice. So let's sort of move off of that. You can see that's sort of a toughie, right? That's sort of a tough one. Just sort of looking around here. Pretty cool. Ah, recognize that one. I think that's is that M20? I think this is yeah, this is the top of the teapot of Sagittarius here, right? There's a globular here, and then there's a big one here. And then M25, let's see if we can pick out M25. Wow, it's really hard to see M25. Is that it? Yeah, that's it. Yeah, okay. It's hard, I mean, there's a lot of stuff here, and to be able to pick that out. Here's M8, the Lagoon Nebula. Here is the Trifid up here. You can sort of see where it is in relation to M25. M25 is up here. So yeah, there's the center of the galaxy for sure. A lot of stuff going on there. A lot of stuff. And as you can see, M25 is south, right? Is a little bit. Here's, let's see. Yeah, so here's sort of the galactic equator, right? Sort of going along this way. and M25 is about 4 degrees south of that. And as we said, 13 degrees or so east of the center. So very cool. Nice little open cluster. Definitely a good view. Okay, audio's good. Good. I've wanted audio in the background for this live stream since the beginning because I think it just it adds. When I watch live streams, it really adds a nice dimension. Otherwise, the background is just sort of flat. The other reason why I'm playing music is because I am having to run one fan on the Linux machine here to keep it cool. So the music sort of, I think, drowns that out a little bit. So okay, let's see. So let's go over to the HST archive, and I don't remember what it's called. HST archive. There it is. And let's see. Should we do IC 4725? Well, IC 4725, and we'll let it resolve. And we'll look at everything. Okay, so whatever that is, let's look at it. Looked at several years ago. Okay, so yeah, they're just looking at a bright star there. So let's try M25. No, we're gonna get the same thing, and that's in the right place. Yeah, so they've never really looked at M25 with the HST. Interesting. Okay, well let's see what they have done with this object. The best way to do that is to look at the papers. Okay, so they found a short period. I don't know what an SB2 system is with a magnetic BP primary. Huh. Well, those are two terms that I don't know anything about. So let's do it. Okay, so let's look at the abstract. I don't know if I like the formats of these abstracts. I mean, I understand they're sort of, saying, okay, here's the context, here's the aims of the paper, here's the methods, here's the results, here's the conclusions. So, they're giving sort of an abstract for each section. Yeah, I suppose that's okay. So let's see. So until recently, almost nothing was known about the evolution of magnetic fields found in upper main sequence AP BP stars during their long main sequence lifetime. Still don't know what an AP BP star is. To obtain observational evidence of how the properties of these magnetic stars, such as the field strength and structure, evolve with age during the main sequence. Main sequence is when the star is that's when stars live out most of their lives. That is the so-called hydrogen fusion stage, where most of the makeup of these stars is hydrogen. And as far as the story goes, in the centers of these stars, fusion is taking place, which fuses hydrogen nuclei into helium nuclei. So the story goes. It's a pretty good story. So one important aspect of this study is to search for rare, very rare examples of hot magnetic stars in short period binary systems. So apparently they found one. So we find that the orbit is eccentric and a period of 17.63 days. The primary is a magnetic BP star. So yeah, let's try to find out what these BP, AP things are here. Magnetic fields have been found in a small percentage of upper main sequence stars since the 1940s. I still don't know what an AP-BP star is. Major improvements in the sensitivity and wavelength coverage of spectropolarimeters have made it possible to search for and study magnetic fields in considerably fainter AP-BP stars than in the past. I don't know what an AP-BP star is. Do we need to dig into that? AP-BP star. So chemically peculiar stars of types A and B. Okay, so an A star and a B star is a pretty massive, hot star. Usually bigger than ours, hotter than ours. But apparently these have an overabundance of metals. Strontium, chromium, europium. They've actually looked for and found europium on these stars. That's pretty interesting. I guess they also have found strong magnetic fields, 33,500 Gauss. So that's pretty strong. I think the Earth's magnetic field is like half a Gauss. I don't know what the sun's is. So the origin of such high magnetic fields is problematic, and two theories have been proposed in order to explain them. One is called fossil field hypothesis, in which the field is a relic of the initial field. Yeah, that's kind of a weird thing. Okay, so they're just very, very, very heavy metal and big. Okay. Oh. Okay, yeah, see, you can sort of see when one component of the binary system is actually crossing the path of the other, and the apparent velocity changes. Yeah, that's pretty cool. So that object is a probable member. So these guys are saying 620 parsecs as well. So yeah, I'm not quite sure what that other number was. I have to investigate that a little bit more. Pretty bright star, right? A V magnitude of 10.18. So that's a pretty bright star. Easily visible. Pretty hot, right? 12,800 K. That's pretty serious. radial velocity, that's radially how far or how fast these objects are moving either towards us or away from us. Of course, we're moving too, so it's sort of a relative thing. But yeah, at least according to this, it looks like it's moving away from us at 5.3 kilometers per second. Don't remember what Sinbad said. I think that was pretty close. Don't remember exactly. I thought that was in the tens? Let's go back one more. I always like to find inconsistencies. Yeah, see, that says 61, and this says 5.3. Okay. So with Gaia, right? They'd be able to go in there and look at the motion of that star and confirm probably beyond a doubt whether it's a member or not. Here they sort of have to say it's a probable one. So there's just all the observations there, taken with CFHT, which of course is not going to exist very much longer, right? It's being taken over by that big spectrometer. They're going to put in a bigger scope. Remember, like it's a Keck size scope with the segments. What was that called? MES? The Mauna Kea something spectrometer. I don't remember now. Chat. Okay, yeah. Hey there, Daniel. Just seeing you in the chat. Got a slightly new format here, so yeah, not looking at the chat quite as much. Hit the thumbs up if you so desire, for sure. All right, let's keep going here. So they're calling it the SB2. I'm going to zoom out a little bit just so we can see a little bit more of this. The lower curve is the mean Stokes. So this is the polarimetric measurement. And okay, yeah, I guess this is a measure of polarimetry. This isn't velocity. Gotcha. Huh, kind of interesting. You can learn a lot from polarimetry, but it's really, really hard. It's usually polarization is a tricky thing, for sure. So I'd like to know what they're. I like to see that they're using IRAF. Good for them. SB2. I really want to know what SB2 stands for. They usually, they mention it once, and then they just use the acronym from that point on. So let's see if we can. I'm not seeing SB2. Yeah, I'm not sure what an SB2 system is. I wonder if Google can help us with that. Okay, I saw it there. SB2. So a SB2 is a double-line spectroscopic binary. And I guess it's a double-line one because of the strong magnetic field? Yes, that's my guess. The wild guess. So, okay, so this is a spectroscopic binary with so they've got a few period measurements here. Very cool. They can do this because they see, they look at this thing, they can't see the individual stars, right? But they notice that over time the spectrum changes. And certain lines all sort of move to the red shift and then move to the blue shift, and you can watch those and you can notice that it's like, or at least come to the conclusion that yeah, it looks like there's probably two of them there. That's kind of a complicated plot there. Orbital phase, of course, is just going around in a circle, right? So from 0 to 1 would be a complete orbit. And they've just extended that a little bit just to help visualize. And here they're measuring the radial velocity from the spectra. So you can see that it's not at 0, right? It's offset a little bit, and that's because of its motion relative to us, right? So this is the 6 kilometers a second type thing. But then you can see that it's doing this kind of thing. So yeah, these two stars are wrapping around one another. Very cool. And it looks like what they're seeing here, and I don't know how good these decimal places are. We'd have to look at the error bars. Okay, well, at least according to these error bars, they've got at least 4 significant figures past the decimal point. So, whew, okay. At least according to their fit, right? They've done a fit to this, and the best fit they can get says that, and that's what the error is. So yeah, that's pretty amazing. Let's see, how many seconds are in a day? There's 86,400 seconds, right? 24 hours times 3,600. Yeah, so let's multiply that by 0.00035. So they're accurate to 30 seconds. They're accurate to 30 seconds on this orbital period. Okay. I don't know what K is. So yeah, here's the radial velocity. Here's the eccentricity. So pretty eccentric, right? That means a pretty elliptical orbit. And of course, they're orbiting a barycenter. So they're, one star isn't exactly stationary, and the other one is going around it. They're going around each other. Here's some other motions. I don't remember what all these are. This might be some kind of mass determination. So 0.4 of a solar mass and 0.3 of a solar mass. Okay. So they're pretty small stars for being magnetic and highly what's the other? Metallicity. Let's see. There's Fortran. Yay. Hail to Fortran. So here's the strength of the magnetic field. Wow, they can actually see the magnetic field varying. I think they do that with polarimetric data. So variations in the magnetic moment. Okay, so yeah, I guess they're just looking at one of the stars and seeing a rotation of 5.41 days. So that's pretty darn fast, right? I mean, our sun, on average, is something like 25 days. Try to keep up with the chat here. Yeah, all hail the Fortran. All right, let's see what else we got here. Okay, so here's... I'm not quite sure what, in this case, what LSD stands for. Can we find that out? Figure that out somehow? Least squares deconvolution. Least squares deconvolution. So yeah, we'd have to actually go into this paper to see what that's all about. And I don't think I'm prepared to do that yet, or at least at this point, I'm not. So yeah, let's just keep going with that. Some kind of data processing tool of some sort. Let's see. So physical properties of the component stars. Okay, so here, yeah, I'm not quite sure what these numbers are then. Orbital elements. Okay, these are just the orbital elements. Has nothing to do with the mass of the sun per se. So yeah, I don't know these numbers really well. But here we go. So this is the ratio of the mass to each of these stars to the mass of the sun. Right, so, okay. This seems a little bit more reasonable, right? The primary is 3.4 times the mass of the sun, and the secondary is 2.3. They're also both brighter, right? Their luminosities. So the primary is a little bit hotter than the secondary, but they're both pretty hot, right? Hotter than the sun. I think the photometric, or, sorry, uh, the photospheric temperature of the sun, I think, is about like 6,000 degrees Kelvin. So they're also, about twice as large as the sun too. 4 times the gravity, makes sense. Okay, so here's some spectra. Very cool. We always like spectra. So you can see that the wavelengths here are in angstroms, right? So going from 4470 angstroms to 4495 angstroms. And we have these absorption features in the spectra, which correspond to various elements: helium, iron, magnesium, chromium, silicon, Nd. Wow, what's Nd? I don't remember what Nd is. More iron. Here's some titanium. Oh, very cool. I don't know why these aren't marked. Kind of strange. Let's see, what are they talking about here? They're saying quite a bit. I think they're just talking about the spectra. Yeah. So they're just explaining how they made all the measurements of the spectra, to determine how much stuff is making all this light. The orbit again. Okay, so they even have a orbital inclination, 30 degrees. That's pretty cool. Let's see what else we got here. So during the course of this project, to obtain repeated spectropolarimetric observations, we discovered the magnetic BP star. So that's very, very cool. This is an actual discovery paper. I like those. So an orbital period of 17.63 days, very eccentric. Mass ratio of 1.479. That's the mass ratio between the primary and the secondary. Well, of course, they use models to understand all these things, and that's okay. Pretty nice. It's a pretty nice, thorough paper. Lots of references. If you ever want to just get lost in any of the history of astronomy, just look at the references to any paper at all, and you will be transported backwards in time, and you can find out some pretty interesting things sometimes. So, all right, well, cool. That was M25. So I think I've looked at M25. Oh man, I don't know how many times, right? But yeah, never. And I mean, we barely scratched the surface here, right? We looked at a couple of pictures, we looked at a couple of papers. There's a lot more to learn. And that's one of the cool things about the universe in general, and astronomy specifically, right? Is that there's just so much out there that, I mean, you can, and people do, right? They spend lifetimes just focused on one thing. Specialization um, inside of astronomy is pretty strong, as it is, I think, with most sciences. It's really hard to cover a lot of different areas, but I think moving on in the future, we're going to have to do that, right? We're going to have to think outside of our little boxes, because I think my opinion, at least, is that we're getting stuck. We're getting really stuck. We're not looking around to seeing what the other sciences can do to help us um, with our work, even if we end up being right, you know, on the path we're on now. I think, thinking a little bit more broadly, and incorporating other ways of thinking and other ways of seeing things um, can only help. It can only help. It can't hurt. We can't keep ourselves in these little boxes. And I see a lot of boxes these days. Cheers. All right, well, cool. I think I'm going to get out of here for now. So thanks for coming in again. Hope you like the new format. I'll uh, I'll continue to work on a couple of these little bugs, because I definitely like to have some panelists down here. But if I can't hear them, can't. Not quite sure why Stellarium isn't wanting to share its screen. There's that. There's for some reason, this graphics card is not being recognized. So not quite sure what's going on there either. I'll have to poke around a little bit. I think if I can get this graphics card working, then I might be able to run OBS. And if I can run OBS, I'm going to be a happy camper, because then we'll have a lot of fun. We'll have a lot of fun. Really like uh, I really like OBS. Well, thanks, Patrick. I appreciate any kind of feedback at all. As I said, I'm trying to get better and better and better and better and better, and along the way you have to experiment a little bit. And being a scientist, that's what I'm all about, right? Is experimenting. So I appreciate your patience, and yeah, I sort of like this. Couple of funny things, but hopefully I'll be able to work those things out in the next few days or so. Hopefully. All right. Well, for now, friends, I'm going to get out of here. Yeah. I'm getting the call. So, all right. I will see you all on the spin a little less than 23 hours from now. All right. Take care, everybody. Peace, cheers, and all that. Bye.